Nearly all schools of art, architecture, and design have classes they call fundamentals, basic design, perhaps even elementary composition. These classes are usually given to bring the student into his initial understanding of how to order space. The best way to do this, I think, is probably to use simple materials, as is usually done. Paper, string, and sticks are usually the things a person begins with. In such a class, several years ago, I began by looking at paper. The assignment was not too terribly constrained. They said something like, why don't you just do something with paper? So I looked around in the classroom and I saw many little, what I'll call knickknacks, and I didn't feel these were too pretty. They sort of had little flowery shapes. And so I decided that arbitrarily I would limit myself to studying what happens in a sheet as you wad it up. Just sort of crumple it, look at it. So by limiting myself to just allowing folding in the sheet, I think there came about a kind of ordering that that carries through the entire work that I've done for several years. I spent probably an entire week just studying wadded up pieces of paper, wadding them up and then looking at the little wrinkles that occurred. And believe it or not, I found some of these wrinkles were quite a bit more interesting than others. This particular one that I finally discovered would both rotate and elevate. Here you push in on it and the central area would kind of twist and come up. I felt that paper had an inherent kind of geometry that if one studied long enough, he could learn something about the way it's structured, this wrinkling. So I began diagramming what I felt were the essential folds that happened in this rather random occurrence. And I produced a diagram that looked something like this. I then simplified this by making what were probably almost straight lines to be straight lines, and if there were triangles that were almost equilateral triangles, I would make them equilateral triangles. There are quite a few less plates involved in this relationship now, but they were what I felt to be the essential plates involved in creating this behavior that you see here. So we're just twisting and rotating upward. You'll note also that there's a kind of wing or leg shooting off the edge there. If one would bring a mirror down here, he would produce a mirror image, as you see this one here. Later, I found that I could produce mirror images along lines of 60 degrees and produce modules that would repeat indefinitely in the two-dimensional plane. Now, this is a diagram of the module we've just folded. I can shrink it down to a pattern like this, and then simply concentrate on this triangular area in the center. I selected this triangle as being one of the controlling ideas of the folding patterns. I then determined that a square and a hexagon folded in a similar way would also be the basis for all of the folding that I was going to do. In the diagram view of the triangular module, one can note two distinctly different things, a set of long legs and a set of short legs. By separating these folded axes in the middle along the long legs, we produce a module that will fold up. Similarly, we can pull apart at the base of the long set, then we can pull apart at the base of the short set, and then again at the center of that, and thus produce parallel expansion through all of the basic axes. These same operations may be used on the square and the hexagonal modules, producing modules that will fold up and integrate into continuously folded patterns. One can score curved lines into the paper and thus develop curved surfaces. You can also fold the paper up with straight lines in such a manner that you achieve interesting curved forms such as this one, which is one of the few that is not a modular repetition. After we've achieved the individual modules, I put them together into groups. The attempt was here to locate a grouping that in 3 dimensions was together, and when you unfold it into the 2-dimensional pattern, is still hung together. Here's a diagram of this 2-dimensional pattern. We will then change it, showing you as you change a single module, what the total effect in the pattern is. This is the triangular pattern. You will note that similar changes going on in it. Once I had determined a modular pattern that would fold up continuously in a single sheet of paper without cutting, I transferred it here to a clean sheet of paper by a pointing process. The pointing process simply involved drawing the initial pattern on a large sheet of paper, laying this down over a clean sheet, and pushing pins through all the apices of the pattern, that is, wherever the lines intersected. The clean sheet of paper then was scored with a blunt tool. I found a worn-out ballpoint pen that no longer left ink marks to be just an ideal tool for this process. The paper was scored in this manner, and then I went over the entire sheet and pinched it either up or down as it was necessary. And you had to keep working over the pattern in this way. You have to sort of fight with it, as you see here, to get it oriented, because the final system is a simultaneously behaving occurrence. So you fight and fight with it, and finally they just fold up. So here we see several examples of triangular modules as they were put into patterns. Some of them are folded down and up, and some of them are folded entirely down. Here are some square modules integrated into a more complex form. And again, some triangle modules in a different pattern. Here are the square modules that we've already animated. The same pattern with a slightly different proportion. The front side of that. And other patterns that don't really relate so directly to these type modular concepts, but may be derived from them. The early work was almost entirely involved with the visual effects of light as it fell across these pristine geometric surfaces. Once I'd played the game of folding up continuous sheets of paper without allowing any cutting, I decided to change the ground rules of the game. That was to cut a module out of this continuum, and after making a whole stack of them, to see if I could join them along some interesting edges. After joining these and thinking they would go into some sort of dome shape, I discovered that only 8 of them would fit perfectly into this elaborate polyhedral form. I had been working so long with plain sheets only, I decided to reconstruct this same assemblage in sticks. Here each stick will represent a folded edge of the module. Here in my hand, I'm now assembling a single, or what was previously, that is, a paper module, and now is diagrammed by the stick module. It's being assembled into this total configuration of 8 basic paper modules. This experiment didn't prove anything necessarily. It did, I guess, make sort of the most beautifully portrayed set of BBs and sticks that's ever been shown. Beyond that, it did give me a kind of means of, what shall I say, of looking at an occurrence, at a phenomena, in a slightly different way. In being able to look through all of these modules portrayed as sticks now, I could see that certain planes would line up in, or certain facets of the modules would line up in one plane. Here, looking down this assemblage, you can see that certain nodes all line up in straight lines. Here again, it's going to line up. These are series of modules now lining up in a single occurrence. It became clear, for those of you who are familiar with certain geometric things, that that there's one-to-one correspondence between the nodes, or as represented the BBs here, a one-to-one correspondence between this and a standard space tessellation known as a tetrahedron, octahedron space truss. It's been used a great deal in architecture. Since I had moved away from the folded paper modules, I noticed that there was no reason to maintain the sticks as representing folded edges. So I decided what we have here are just a bunch of points in 3 dimensions that have certain symmetry properties, and now let's visually portray a variety of ways of ordering these series of points in space. One could join them with gelatin here and indicate 2 interlocking tetrahedra. The one diagrammed with red gelatin and the other one not diagrammed, there with the apex in my lower hand. Then you could remove this gelatin and hook together a different grouping of points with new pieces of gelatin and produce very, I felt, exciting visual symmetries. This was, strangely enough, my front yard in Iowa City. Now those aren't very bad patterns. I think they're rather nice. They're just the gelatins on this framework with the sunlight shining through onto the sidewalk. Now once again we're going to shoot through this assemblage up into the sun. I'd like to remind you that that we started with one module of the several that we've already looked at. And these elaborate forms could be produced with any number of these modules, in combinations or in repetitions of single modules, and produce literally hundreds and thousands of elaborate structures. After I built a number of the stick assemblages, I discovered there are such things as polyhedral forms. The simple polyhedrons are called platonic solids. The simple ones are the tetrahedron, the cube, and octahedron. I discovered once, while working with some of these simple forms, I could perform the following operation. I could diagram the initial polyhedron, in this case the octahedron, and perform an operation of drawing lines, or in this case putting actual members, from every apex to an adjacent or opposite face. When this operation was performed and all the linkages were joined together on the faces, the following sort of movable thing would be solved. This first model is not actually the octahedron study, it's the icosahedron. The icosahedron has 20 equilateral faces and 30 apices, very complex in relationship. This is the octahedron study. It makes a very interesting movable toy. In fact, I've often wanted to see it produced as a kind of three-dimensional building block and integrated into a three-dimensional network that actually moved in this fashion. I discovered with some further studies that I could put a series of equilateral triangles on certain sets of these nodes, and it would open and close down to the original octahedron shape. And you'll notice as it opens here that the extreme opening is a square. It's possible also to remove the equilateral triangles and put on squares on these nodes that are coming out through the holes and have the thing close down into a cube. Recalling from the early part of the film where we had the triangular folded paper pattern, I now want to remove the triangular module from the pattern, leaving just these triangles. These triangular modules were hooked together with tape in a wooden model, as you see here, and produced this rather random, uncontrollable motion. One could pull it apart and move it around in this way and get a rather interesting behavior from the system, although it wasn't maybe always so easy to get it put back together. Some tests, in fact, showed that 3-year-olds could do it in 10 seconds and 5-year-olds could do it in 12 seconds, and adults sometimes failed. But I, with some experience, did get it back together and went on to try some squares hooked corner to corner. And here I collected a lot of milk cartons and taped them together with Scotch tape on the edges and found that I could get a controlled behavior out of this motion. Then, wanting to extend this idea, I went from corner to side in this scene, seeing whether I could get this motion. Although I felt this is kind of cheating because one can draw lines from all the points and produce diamonds with just little triangular ballast on the side. So really we're getting still a kind of corner-to-corner pivotal connection in these systems. Went on to produce this movable geometry out of styrofoam and filament tape for connectors. I discovered in looking at these movable systems later that I could extend any of them into long prismatic forms, as this network. This is the same as the milk carton network, a series of squares. When you extend them, you can slice down through them. Here's the slicing plane, and opening again, produce this rather peculiar crevice condition. A little further study of these systems, and I found that the groups which were not mechanically controllable, as the triangular one that we began with, could be made to be controllable if I would hook it with what I'll call its inverse, which is produced by an identity operation and rotation of the second group by 60 degrees in this particular one. You'll note that an upper module of the gray network is coupled pivotally to the center of a lower module and rotates in the reverse order. I'm also beginning to discover that these ideas are occurring in a two-dimensional plane, and as soon as one discovers that, he must go to 3 dimensions. My first attempt to do this was to hook linkages to the corners and maintain the rotational motion of one module above the next, but in this way to get an elevation. I did this in the triangular network, and here you see the result in this wooden model. And this close-up shot looks something right straight out of Gulliver's Travels. And at the end of the film, in fact, we'll raise the rather tricky question of how one would spread this network across a spherical surface and make a curved dome with modular repetition. Further studies of this nature of interconnecting three-dimensional linkages produced this system. I feel it's more consistent. The previous ones were sort of concepts in planes with interconnections, and this one, though, is hooked in a very consistent way on all of the corners. And any way you go through it, it's the same system. It will open up with space all around each cube and then close down to be perfectly tightly packed. I made larger and larger models. This is become known as the famous Atlas shot, where I'm holding up the world. This is a system of about 85 cubes, and they're all hooked corner to corner. And you can conceptually notice that as you grab a hold of one and twist it or rotate it one direction, all the cubes connected to it will rotate in a parallel fashion. That is, the axis of rotation is parallel to this one, but they rotate in an opposite direction. The top view looks very reminiscent of the two-dimensional pattern, but it really didn't help me to discover this. Although later you wonder why you didn't discover it more readily. The design problem here was how to hook together all of these cubes, 8 connectors on an individual cube, on a very simple basis. I solved it with rope in the first model. And later, wanting to mechanize it, I discovered I could actually run a bent wire cam down through the edges of all of these. And so this system is produced by rigid rods just bent at the corners where they're connected. A rather surprising result. I never anticipated I could have done that. Here we're branching now to a totally different concept. I had this Mexican stool in my apartment for some time before I discovered that if you drew lines around the extreme nodes of this, it would inscribe in space an octahedron. And I knew that octahedrons with little tetrahedral gaps would go together to fill space in a network. This definition, however, would close up into a line and open back up into the octahedron. So if I made several of these and put them together, I would have octahedron opening up in a coordinated way. And I discovered with this simple little three-dimensional sketch that I could make them move in a coordinated way. These opened up in a rather flat way. The centers of fulcrums were on the measured center of the rods. Well, what would happen if you put lots of them together and you also moved this fulcrum off-center in the center of the rod? Once again, in the absence of parts, I'm going to have to make all these joints, and these were all silver soldered together, little Y-shaped hinges, and put them in, put all these linkages together. And when I opened it up, I discovered that I could produce a dome with this type of network. And the curvature of the dome was directly related to the eccentricity of the central fulcrum off of the measured center. It opened out quite nicely there, and you could then close it back up into sort of a bundle of sticks. It would open also in a kind of planar sense and looked, in this case, very much like a convertible top mechanism. And then you could close it back down, and it folded up and ran nails right through my fingers. Well, for some time now, I'd been working in a kind of blank or blind alley approach, kind of pure attitude toward just investigating things as they happen. And one would be asked continually, you know, well, just what are you going to do with all that? I began to wonder myself. So I began to turn my attention to trying to find practical, whatever that is, practical applications for some of these continuous geometries. The first thing I tried was a textile-covered acoustical wall panel. This is a vacuum-formed panel without the textile covering. You can see that it's developed from the initial triangular geometry. The process is one of producing a mahogany die in order to do the vacuum forming. Here you see the mahogany die. It's made out of hundreds of little wooden pieces that I cut out on a table saw to simulate the precise geometry of the folded pattern. This geometry would allow one to roll textile out in it and tamp it down in the crevices just slightly, so that you needed no material drawing in from the outer edges, but all the material is available in each individual crevice, which I'm producing here with a naga hide to demonstrate that it doesn't have to stretch. When we finally vacuum formed, we rolled out a blue wool material in much this shape, and then heated the vinyl above the die and brought it down on top of the wool and the die, and through the vacuum forming switch, and in just a second produced, as you see, a rather luxurious blue wool covered panel that had both decorative and acoustical properties. Ultimately, these panels could be produced with a soft foam backing that would allow them to be rolled up in bolts and sold by the yard. Now let us turn our attention to the functional possibility of these folded paper forms. Hardly anyone saw these early paper forms without imagining them as finished structures. So for the next several years, I'm going to try to solve the problems of going from these paper models into actual buildings. I didn't really intend to build structures, that is, finished buildings, by actually moving them as I'm doing with the models. What I do feel is sensible with these kinds of systems is in the design stage, you may move the buildings around, and once you have determined the actual shape you want to build, then you go out and build it. If one is going to build buildings with this kind of flexible geometry, that is, in the design process at least, he must be able to determine the openings across these crevices. You see the small, rather three-pointed star-shaped forms on the surface? You'll notice they open and close in order to allow the total form to assume some given shape. If one can determine, then, the distance across these folded crevices, here represented in the stick diagram, and sort of measure between these three nodes, and go through all the pattern that way and determine the measurements, he could fix in a rigid manner the entire structural system. So I began, since I was not a mathematician, to build more and more models and study the behavior of the folding as I would move it from one form into another. Here again we see the crevices as they open, and you'll notice that although we have a large amount of economy in the initial folded paper pattern, in that there are only two uniquely different triangles, an equilateral triangle and a 30-60 or approximate 30-60 degree triangle in the crevices repeated 6 times, we do not have identical measurements going across these gaps for any given form that we achieve. So I began to build large models and tried to take measurements from these. Here you see a different geometry producing a slightly different dome configuration. I assumed that by building larger and larger models that I'd reduce the error in measurement. This structure was produced rather crudely because I didn't know quite how to fold a 1/4-inch piece of cardboard, so I started by using a sledgehammer and a piece of 1/8-inch cold rolled steel on edge and beat every inch of the scoring into this thing and folded it up. This model was much too crude, and so I tried to refine the process and spent some time investigating how people produce boxes. And borrowing their techniques, I developed this scoring technique I used this scoring die from the manufacturers. In the absence of a large stamping press, such as General Motors might use for a car top, I developed this somewhat crude but very effective press. And with the right people on top, if they didn't fall off, you could score a sheet with just enough pressure for scoring and not so much to cut through it. Then once again, I have to break the folds in so that they're oriented in the proper direction. This was a kind of judo chop I developed. And go around and finally fold each sheet up. These are kind of captured film from my early student days. Then these sheets, as they'd been folded up and broken in, were put down on the floor and butt jointed and taped on both sides so that we're going to simulate the continuous sheet geometry on a large scale. The model, when it was finally put together, was a little over 24 feet in a room that was 22 feet wide. And then we went around and began to fold up the pattern in a sort of large salad bowl shape. The ropes on there are to relieve the tension. When we first start folding, it's a little unstable. But as we proceed on around, we get it pulled into shape and then turn the whole structure over. It's then about 20 to 21 feet in diameter. And I began to insert, as you see here, these plates, which I assumed I'd have to put all over the dome. But the dome had so much resiliency in the cardboard that the net effect of having it contained with a tension ring all the way around the outer edge was it actually blew up, and you can see the tape, we had to hold it down where really there should have been compression members. These paper structures had not provided enough information from measuring them because they would not remain in a stable position so that I could determine anything. So I sort of locked myself away in a room for a few weeks and began building these stick models that demanded the measured inserts in order to even hold up. You can see they didn't hold up very well. But as I would build these and they would collapse, I would tiptoe out through them and measure the point that had collapsed to see whether it was the insert was too long or too short. And I would go back out and put this on a chart and either lengthen it or shorten it as it seemed appropriate. After a while, I got a rather intuitive, qualitative notion about what was happening. It seemed to me that the cross-section of the dome was a certain type of curve, and the curve, as I kept track of these measurements, had the same character. So I plotted on the computer a sequence of measurements which I went back and inserted, and this produced a much more uniform surface, although even this approach began to dwindle as it was only a quasi-mathematical and intuitive approach. With this in mind, however, I approached the computer people again, who had said earlier that they couldn't help me because the mathematicians who were working on the problem had written a system of simultaneous equations in the third degree, which they informed me there was no known solution of. I found that very entertaining. But I've come to appreciate that problem in recent years. Anyway, when I approached the computer people and showed them that I could solve the problem by myself with a few sticks, they said, fine, well, maybe we better think about this again. If you can simulate the problem physically, why can't we write programs to simulate this on the computer just as you would build it? Rather than start with the folded paper problem, I started with a subset. These equilateral triangles you've just seen spread across a sphere. One wants to know how to determine that geometry precisely. Being familiar with Fuller's work and his insistence that any behavior on a sphere was a geodesic occurrence, I built this paper model of a geodesic projection. On the table would be an equilateral grid, and below it, the center of a sphere. The projection of rays from the center through the equilateral grid will result in this white paper network that I'm constructing. The outer extremities of this projection, as it intersected the sphere, creates the geodesic dome, or the geodesic projection. Since I had learned how to compute this, in fact wrote a program to compute all the possible ways of determining geodesics, I wanted to find out if there was any relationship between my triangular movable pattern and the kinematic structure, because then I could compute it. So I'm building this model of the geodesic projection, and then I'll lay onto the geodesic network represented by these outer edges of the white paper my triangular pattern. The question is, do the centers or the apices of this movable triangular network relate in any way to the nodes of the geodesic projection? It turned out, of course, well, I don't know why I should say of course, it turned out that they didn't. And so I had to go on and continue writing a program which tried to determine in a heuristic way, that is, you don't know the solution that you're shooting for, but you know it by making a guess and then correcting towards what you think is the solution. This program moved the triangles in some angular way, and then looked at where we were and said that isn't quite correct, and rebuilt it, and yet adjusted the angles slightly. So I spread the equilateral triangles out on the spherical surface in this manner, and I wrote a program to make perspective drawings. Once I could make one perspective drawing, of course I could make many. And so I produced thousands of these drawings on paper, registered them on animation stand, and in this way produced this first very crude animated film. There you see the equilateral triangles on a sphere, and now we'll see the inserts, or the non-identical measurements in the network. And once you can produce one network, of course you produce two, and look at pretty flower patterns as the moire patterns overlap. And now we'll bring this back and turn it over on its side, and we will have it in a condition much as we had the early triangular wood form, only rather than being flat, we'll have these two systems on a sphere. Then I'll shrink this so that we have one system on a concentric sphere with a smaller radius, and we can interconnect them again with these non-identical linkages and have a very stable and yet modular reproduced structural truss. 9 years ago, I began by folding paper, as you've seen. Some 5 years ago, I just finished the computer animation you saw, which is relatively crude by our current techniques. Just recently, we've been able to solve this problem that I've posed many years ago of how to determine the simulated geometry of the paper fold so that I can actually construct it. I'm now able to sit down in a cathode ray tube, to bring in a simulation of the paper folding, and to design up any sort of structural shell that we want to build, also to do the structural analysis. At which time, if we're pleased, we can make drawings. Here are a few of the drawings that we can make. If we don't like it, we can modify them and go on to make others. I've gone on to become further interested in not only the simulation of the geometry of forms, but the simulation of their visual effect. You'll recall the problem of spreading these equilateral triangles only on a sphere, and here's a modification of that problem. This model is determined in the computer. It does not exist. It is then simulated in tone and color, as you can see, entirely by computer and printed on photographic paper. Here is a second photograph of such a picture. It is also a three-dimensional model, by the way, and does not exist. It is a basis on which I can do sculpture. Continually people ask me, now that I've solved the folded paper problem, why it is that I stay with the computer business. In fact, many more people ask me, how is it even possible for an artist to relate to the computer field and to do research in that area? In view of my work in terms of the months and years that I've spent fabricating models after I asked myself some question about a geometry, it seems most natural to me. Design is a kind of feedback loop between the artist and the environment, between the designer and of some posed problem. It seems that the person is always in a position of saying, I wonder what will happen if, or he looks at a problem and says, perhaps this will work, and he goes out and tries something. The environment responds by collapsing quite often in his proposed solution when he fabricates it, and then he makes modifications and goes again. And this kind of loop keeps going back and forth. In the interim, though, there's not much information. There's just a lot of labor and a lot of expense. It's my hope that the computer can become a medium in which these posed ideas, posed solutions can be tested out, and the information coming back from the results of this posed solution can be modified. The computer can really speed up this kind of design loop, and I think greatly aid creativity. The excitement for me is to try to develop the computer then as a medium for exploration and as a medium for expression.